The question regarding the halogen bond is that when we co-recrystallize the iodine molecules with other two type of aromatic molecules, we have linear polymeric chain structure, and the the iodine bond length is shifted from 2.715 to be 2.733 and 2.722. Right. So I want you to explain why iodine bond length is shifted in this style, in this way. Okay. So you have to use halogen bond interaction to describe all about this. Okay. If you haven't done it yet, you have to do it right now. Okay, by pause the video here. Okay. But if you finish, just continue the video. I will give you the correct answer for this. So as I said, everything happens by theory. Halogen bond is orbital interactions, and this is confirmed by the experiment here because the bond length is shifted. So if you compare the first two pair, right, iodine has stronger bond order, 2.715, shorter bond length. Right. So if you have interaction with this nitrogen, the bond length is longer. That means the bond order of iodine is weaker. So if iodine bond is weaker, that means you have orbital interaction. Don't forget that this is a sigma bond. So if this is weaker, that means you fill electron into sigma star orbitals, into the LUMO. Right? Because when you calculate the bond order, it is bonding minus anti-bonding divided by 2. So if you partially fulfilled or partially fill the electron in the sigma star orbitals, so bond order is decreasing down from 1 to something to 0 point something, and hence the bond length is increasing. So if you want to fill electron into sigma star orbital, you have to look at the sigma star orbital of iodine. So you know that sigma orbitals of iodine is from px and px if the x is the bonding axis. So I have to erase all this out a bit. So sigma is from px and px, right? So sigma star of iodine, you're creating a node, right? And then by negative combination, by the phase of electrons, no? So this is sigma star of the iodine. So if you want to elongate the bond order, the bond length, you decrease down the bond order. So that means electron pair of nitrogen is put here into the sigma star. So this is 180 degrees. And this is the orbital interaction. Right? So with electron pair of nitrogen donating into the sigma star orbital of iodine, you're weakening the bond order. And then the bond length is longer from 715 to 733, right? A bit longer. So as you can see, you are now like nitrogen, right? Electron pair, and then you donate the electron from the nitrogen atom here to the sigma hole, right? To the sigma star orbitals, okay? And yeah, this is the interaction between nucleophile and the sigma hole of your halogenated hydrocarbon here. And yeah, it's the same thing with the hydrogen molecules. But now, when you put methyl group 4 of the methyl substituents on the benzene ring, on the aromatic ring, you still have the interaction over here. But if you think about the methyl group as the electron donor, right, that means you're increasing the electron clouds in the molecules. And so, if the electron is higher, electron density is higher, interaction should be better, right? Because the electron density interact with the sigma positive. It should be stronger. And if it is stronger, you can then elongate the II bond better than this. And the number have to be more than 733. But surprisingly, Actually, it's not surprise for me. Surprisingly, it's less. It's 722. Why? Because if you still understand the donation of the methyl group, right? The electron donation is not really affects here in your system. Because if you have the methyl group, right, the donation of the electron is hyperconjugation effect to the p electron pi system. But the electron which donating to iodine is not in your pi system. Right? 4 of the methyl groups is electron donor to the pi system. Right? And it's good for electrophilic aromatic substitution, things like that. But electron pair interacting with iodine is in your sp2 orbitals, right? Because you are talking about electron pair here in sp2, not in your p orbital, not increasing by the hyperconjugation effect of the methyl group. So actually, the methyl group has almost no effect with the electron clouds on sp2 nitrogen atom here. Okay. So the effects you see from here is actually very, very simple. It's a steric effect of 3 of methyl group. Because iodine is so huge, right? Iodine is in group in period 5, so it's so huge. So instead of having hydrogen atom, you have methyl group. So it prevents the orbital interactions because it's so steric. The bulkiness, right, blocking the interaction. So the donation is worse comparing with the upper one, with just hydrogen atoms, which is very small. So nothing can block the iodine from the interactions, right? So as you can see, if you have bulkiness of tetramethyl group in the molecules, then the interaction is weaker. So if the interaction is weaker, electrons that partially filled into sigma star orbitals is worse, right? So bond is still quite strong, right? Quite strong. So this is why the bond length of iodine is shifted. So you can explain it by molecular orbital theory, right? On the basis of halogen bond.